Okay, good afternoon. Before we begin, I just want to let you know the test is in clip, so you should have the date there. So it will be on April 11 during the time slot of the tutorial, like it was last year. And this is the end of this first part. So this first part that I'm lecturing is a bit more theoretical to give you the foundation, and then the second part with Professor Rui Rodrigues will be for the final assignment, will be more hands-on. So this first part will end on April 11, and the test will count for 30% of the final grade. The lecture slot on April 11 will be to review and for your questions about the test, and also to help you start with the tutorial, which is the first assignment. So 20% of the final grade will be a TensorFlow tutorial, optionally with Keras too. We're going to talk about that next week, but mostly TensorFlow, which is the more complex part. And this is for you to basically to help you get ready for the final assignment. So although this only counts for 20% of the final grade, it's useful for the final assignment for you to structure what you know about TensorFlow and Keras and so forth. That the deadline for the first assignment is the eve of the first session you'll have on the second part. So there will be 2 weeks without lessons in this course because of the holiday and so on. So there is an interval of 2 weeks, and the deadline is on May 1st for you to submit the assignment. I will put the instructions on the web page maybe next week, but basically you send everything by email from your FCT account. Okay. So this first assignment is individual. Each of you will do their own. The second assignment we're still not sure because everything must be graded before the exam, and you're more students this year than last year. So maybe the second assignment possibly will be in groups of 2, but Professor Rui Rodrigues will let you know when he decides. Okay, so for today, I'm going to start talking a bit about differences between shallow and wide models and deep networks. Then we're going to look at the vanishing gradients problem, so one of the stumbling blocks for training deep networks until about 8 years ago, something like that. Then we'll talk about the rectified linear units and different activation functions that we can use on neural networks. And how we're going to choose different activation functions inside the network for hidden layers and for the output layers. So first, let's consider differences between having a wide, shallow model or a deeper model. And I'm going to start with this theorem, which is the universal approximation. So imagine that you have a function that is non-constant and continuous, and you have a volume, but this is a unit volume. So a unit volume, but you can generalize for whatever you want. That m there is the number of dimensions, so it could be the number of inputs, and you have some function f that is continuous within that volume, but has some shape, some arbitrary line that we don't know what it is. So Savenko proved this for where theta is where phi is a sigmoid function. So if you had a sigmoid there, but this can be generalized for any nonlinear function here. But basically, what he proved is there is a number of n constants for these weights here, w, this bias b, and this weight v, where if you add basically a linear combination of the inputs passed through this nonlinear function, and then make a linear combination with a number of these functions, there is a finite n that you can choose with the appropriate weights that allow you to approximate this unknown function f arbitrarily within that volume. So this is a bit esoteric, but what this means is what we have here is basically a neural network with one hidden layer and a linear output. So these are the inputs to the neurons on the hidden layer. Each neuron will fire according to that activation function, and then we have a linear combination of all these neurons for the output. So if we have one layer of neurons with a nonlinear activation, and then one final neuron with a linear activation, simply computing the linear combination of all the neurons in the hidden layer, we can arbitrarily approximate any function within a fixed volume. So that one could be any constant. We cannot do it to infinity, but as long as we decide on a box where we want to approximate that function, we can approximate it. So this is the universal approximation theorem, and basically it proves that if you have one hidden layer, you can arbitrarily approximate any function within a bounded region. So basically, for most purposes, we would only need one hidden layer. However, there is a difference between having one hidden layer or many layers and creating a deep network, in that with fewer neurons you can create more oscillations with a deeper network. So you could approximate any function with only one hidden layer, but if you stack layers, you can make the function curve more tightly and have more oscillations, more curves. And this is useful for classification because it relates to this Vapnik-Chevron-Jenkins dimension. So some of you already heard about this. I'm just going to review it. But imagine that we have a hypothesis class or a bag of possible ways of classifying our examples. So suppose that our hypothesis class is the set of all straight lines. So we can pick any straight line in order to create a classifier. And we can say that this hypothesis class shatters a set of examples if for any labeling of those examples, at whatever class we assign them to, we can always find one way of classifying them correctly. So, for example, consider a set of 3 points in a triangle like this. We can say that the set of all straight lines shatters this set of examples, because for any labeling that we assign the 3 points, we can find a straight line that separates the two classes correctly. So we have one trivial case where they're all blue. A lot of lines will do for this. Then one red and two blue in different combinations, and all red and so forth. And the other making two reds and one blue is the same thing. So this is the Vapnik-Chevron-Jenkins dimension, the largest number of examples which can be shattered by the hypothesis class. Note that if you put 4 points, there is no way of putting 4 points on the plane that allows them to be shattered by a single line, because there will always be some combinations of labels that you cannot separate with a straight line. So this is the maximum you can do with a straight line. If you have functions that curve more tightly, that oscillate more, you can have, in general, higher Vapnik-Chevron-Jenkins dimensions. You can classify correctly more complex and larger numbers of points. So this is basically one way of understanding what's the use of having deeper networks. Although we could theoretically approximate any function with just one wide hidden layer, we would need lots of neurons to do the same kind of oscillations that we can do by stacking several layers. However, there is also this theorem, or this set of theorems, the no-free-lunch theorems, because this is more generic for optimization problems and so on, which basically tells us that if we consider all sets of possible distributions, or all possible distributions of data, for any number of cases where algorithm A performs better than B, there is an identical number of cases where B performs better than A. This doesn't matter what the algorithm is. So basically, for all sets for all possible distributions of data sets, on average, all algorithms perform the same. The thing is that in real life, data is not distributed in all theoretically possible ways. So the data has some structure, some correlation, some specific distribution. So for specific problems, some algorithms are better than others. And this is, when we put these things together, the basic idea is that deep neural networks have some properties that differ from wide neural networks, although both could theoretically approximate any function arbitrarily, but for some problems, some are better and others worse, and vice versa. So basically, the best algorithm to use will depend on the problem that you have, and there is no general recipe for always use this kind of method. When you use shallow models like linear classifiers or even linear with some non-linearity but not very deep, there are some advantages in that they tend to be better at memorizing interactions between features. So if two features co-occur, this can be immediately reflected in the weight, but it's harder to make them generalized. So for example, this kind of recommendation, customers who purchase this also purchase that product. That is easy to model in wide, shallow models. But it's hard to see, for example, that people who like horror movies also like thrillers, unless you engineer the features and put the classifications there and actually put those features in. So horror movies and thrillers, in that case the model can find out because it can spot the correlation between these features. But it has no way of knowing that, for example, thrillers and horror movies are similar, or that one movie is similar to another, or something like that. So these are advantages and disadvantages in using shallow models. When we use deep learning, then deep models are better at learning relevant features even without specifically engineering them in. And they can figure out that some things are similar or dissimilar even without spelling them. But then it's very hard to understand what exactly the model is doing. So this is a few years ago, it was a bit popular on Twitter, which were images of similar things. For example, chihuahuas and raisin muffins, or these sheepdogs and mops, and puppies and bagels. They look similar. And it's very hard to tell if you train a neural network, a deep model, to identify images. You cannot tell a priori if it will be confused by this or not. You have to try it experimentally, because the way things then are represented inside, you don't know which features the network is using. Whereas if you have a linear model, for example, and you have the features, you know exactly which regions of the feature space it will classify in one side or the other, so you could figure out these kinds of things better. So this is a disadvantage of deep models, is that they're black box, and you cannot predict what they will do unless you experiment with them. And there are some you can find online some empirical studies of this with different image recognition networks. That some of these, for example, they confuse muffins with stuffed animals and put in different categories. Others can actually distinguish and do not make those mistakes. But you cannot simply, looking at the classifier, determine how they work unless you experiment. So to show an example of these trade-offs, this is an interesting paper from 2016, in which the authors, instead of choosing between using a wide model, which is a logistic regression, so it's a linear classifier using a large number of features, or using a deep model with dense embedding and then a multi-layer pattern at the end. This is for a recommender system for Google Play, the online store. They actually combine the two, so they put the two in the same system and combine things together. And the explanation they have is that, and you can find this online, So you have a link here for an explanation of how the system works, but also you can look at the paper. But the idea is that the shallow model can pinpoint associations between categories. They don't use the real examples because there's a lot of money involved in recommending on Google Play, so they use some hypothetical food store, but it would be something like understanding that people who want fried chicken may also choose chicken and waffles, but don't want fried rice with chicken along with fried chicken, even though they have the same kind of string. But with deep models, you can find, for example, in the embedding, that fried chicken and hamburger occur in the same region of the feature space that the deep model learns. So even if nobody ever asked for a hamburger in some particular situation, the model could find out that it was similar to what people who ordered fried chicken had also asked, and could use that for novel recommendations. So basically, a shallow model is good at identifying these correlations and recommending to someone what other person has already done, so using the same recommendations. But deep models can go beyond that and try to figure out similar recommendations and not exactly some things that people already did. So they can put some novelty in the recommendation, although with some error. So to optimize that, they put the two together and could actually increase about 1% over the deep-only model and improve the app acquisition rate 3.9%. So when you consider the 1 billion active users there on the shop, increasing 3.9% the amount of money they spend is actually a very good result. So even though 3.9% doesn't seem impressive, it depends on the application. Okay? So this is an example just to show you that even though we're focusing on deep learning, it's not necessarily the only solution that you'll get, and you'll have to look at the problems and try to figure out which is the best way to approach them. So basically, the two main factors here that you have to juggle are the effort needed to engineer features, which is much greater when you use shallow models because they need carefully engineered features in order to work. And on the other hand, how intelligible, how understandable the model itself is. If you use deeper models, then we have no idea how they work or what they will do unless we actually experiment. So these are the two trade-offs most of the time that you have to make. If you have very good features, then probably a simple model is best because then you know clearly what the model is doing. If you have no idea how to extract features, and this happens, for example, when you're doing image recognition or working with sound or unstructured data in general, in that case, deep models tend to be better because we don't have good features for the others. So what was the problem until fairly recent with deep neural networks? This is the vanishing gradient problem. Comes because we need to assign to each parameter of our model some responsibility for the error in the output. And we do that by using the chain rule and multiplying the gradient over all the functions that we're using. So this is, just to recall, the backpropagation. We start from the last neuron, and then we propagate the error to the layer before the last one, and the layer before that, and so forth. And you see, over these steps, we are multiplying derivatives of the function. So one problem here happens with this kind of activation, such as logistic activation or hyperbolic tangent activation, which have that shape that saturates, and you start getting derivatives close to zero. So you can use them with a single layer. This is TensorFlow playground. You can use this to experiment with neural networks, and you can choose the data set that you want. You can choose the dimensions of the network, the kind of activation. So in this case, I use sigmoid, one hidden layer with these 8 neurons, and it works well, and it manages up to 370 epochs. It can classify the data set well. But if I use a more complex data set, so this with spirals, one hidden layer with 8 neurons doesn't work well, and if I increase the number of hidden layers, then even after 1,400 epochs, it's still not working. So even increasing the number of layers, it's not giving me any results. And the reason for this is that, well, increasing even further doesn't work either, so it's kind of getting stuck. Here I went to 2,000 epochs and nothing happened mostly. And the reason for this is that this kind of activation saturates at the extreme. So when the neuron is firing, if it's firing more intensely, then the gradient tends to 0. And if we have very many layers of these kinds of activations, then when we use this propagation of the gradients by multiplying, we'll have lots of zeros appearing there, and all these multiplications, so our values very close to 0, and then everything goes down to 0, and there is no information for the optimizer to optimize the parameter. So this is the vanishing gradient problem, where the gradients start to disappear, we lose information, and we cannot continue the optimization. So this was a problem until about 2010, 2009. There were some attempts to overcome this with pre-training the layers independently, and we're going to talk a bit about that in the next week. But what saved the day was this rectified linear unit. So with sigmoid activation, we have a curve like this. This will tend asymptotically to 1. With a hyperbolic tangent, it's a similar one, only it goes from -1 to 1 instead of from 0 to 1. But these were the typical activations used that had this vanishing gradient problem. A rectified linear unit is just this. If the input, the combinations of values multiplied by the weights, the sum of the inputs multiplied by the weights, this x here, is below 0, then the output of the neuron is 0. If it's greater than 0, then it's simply x. Whatever comes in also goes out. This is not at all what would model how a neuron works in the brain or something like that, so that initial inspiration for neural networks has nothing to do with this. But this elbow here is enough to give that non-linearity that is necessary so that linear combinations, when we pass on to the next layer, are not just a linear combination in the end. So if we use an identity function as the activation and we stack layers together, then the result will just be a linear combination of the inputs. There is no non-linearity there. It's the same as just using one neuron. There is no advantage in doing that. But with this elbow here, that's enough to make it sufficiently non-linear so that now it works as a deep network, and we can make it learn more things. And now with this, if we use a sigmoid, we cannot learn anything even after 1,400 epochs. But if we use a rectified linear unit, it quickly learns. So the 200 epochs, it already classifies the data set correctly. And the reason for this is that this derivative here will not vanish. It's always 1. So there's always information about how to change the parameters of the neuron and learn. So we can even increasing the layers for hidden layers, 200 epochs, and it still learns. And so if we do this with a rectified linear unit, we can stack many layers and still the thing will work. So this was really the breakthrough for deep learning using rectified linear units. There were some approximate solutions before, also better optimization algorithms and so on, but this really made a big difference. With rectified linear units, you can train many more layers. Besides that, a rectified linear unit is very fast to compute because we just need to check if it's below 0 or above 0, and if it's above 0, it's just x, so you don't have to compute anything, unlike for example, the sigmoid function, where you have those exponentials or tangents and so forth. And since it does not saturate, the gradient is constant, you don't have the vanishing gradient problem. One disadvantage of rectified linear units is that the neuron can die. And this happens when, if for the training set, the weights are such that in all examples in the training set, the neuron will have a next, so the net input here is negative, then this neuron will always be on this side, on the training set, so its gradient will always be 0 and the weights will no longer change. So once this happens to a neuron, then it gets stuck and will no longer be able to change because the gradient there will always be 0. So this happens to rectified linear units. They can die if by chance they fall into that state. This may not be so bad if you have a large network and may result in a sparser encoding there, but there are variants that fix this problem and actually work better. So now I'm going to show you a few variants of rectified linear units. This is the basic one. We can have a leaky rectified linear unit, and the leakage is there with this additional parameter that gives us some slope, a small slope in the negative part. So it's again non-linear because of the elbow there, but since the gradient on the negative part is not exactly 0, it's still able to learn and recover or to adjust the parameters. And these actually work better than rectified linear units, the standard one. Then you have variants here. One thing to note and to be careful about is that sometimes the leaky rectified linear unit is represented in this way. So you have a fraction of x in the negative slope. Sometimes you have the constant is the slope there. This is the case in TensorFlow. So if you see in some paper the leaky ReLU with alpha of 100 or 20 or something like that, then you know it's this one because it would not make sense the other one. But if you're using it in TensorFlow, remember you have to multiply by 0.1 or something like that, and that would be the parameter to use. Other variants, parametric rectified linear unit is the same as leaky, but this alpha is also a parameter that is learned, so it's adjusted for each neuron with the data set. Then you have randomized leaky ReLU, which during training you draw that alpha from a random distribution, and when you finish training, then for classification you use the expected value, you use the average of that random distribution for the alpha. And well, you have lots of different possibilities for rectified linear units. This is an example from 2015 comparison here. You can note that the leaky rectified linear units here compared, one has alpha of 100, the other of 5.5, so this is actually the diff notation here and not the one as in TensorFlow. But you can see that in general these leaky rectified linear units work best, and you can check many different comparisons of this type. In any case, this also depends on the data, so usually it's a good idea to try different variants to see which ones seem to work better with your own data. There are other options. For example, concatenated rectified linear units use the output of conceptually two rectified linear units, one on the positive side, one on the negative side, so you don't have this small slope here. You have two slopes of -1 and 1. The exponential linear unit is linear on the positive side, and then using this exponential function here so that it's not only continuous but the derivative is also continuous. This, in theory, could have some advantages on the minimization. In practice, it doesn't seem to be an advantage, especially because this then will take longer to compute, much longer than the rectified linear unit. So, in any case, what you find, if you look at the literature about these options, is basically that in some instances, one of them seems to work better, and usually the authors that propose a specific one find the instance where their proposal works best, But then what you can see is that it depends a lot of the data and other conditions of training and the data set and so forth. So basically, remember the no free lunch theorem. You should test different options if you want to really optimize your classifier or your network, and test different options to see what works best. So, which activations should we use and why? In the hidden layers, what we want is a nonlinear transformation. We need that, otherwise there's no point in stacking the layers. But it should be fast to compute, and it should not be subject to that vanishing gradient. So, rectified linear units are good. If you use the standard rectified linear units, there is the danger of dying during training. So, if, for all examples, the x is negative, then the neuron will get stuck there. So, you should use leaky variants, but this is the recommended choice for hidden layers. All you need, the hidden layers neurons just need an activation function in order to break the linearity of the transformations, so that the stack does not just become one linear combination of the features. There are some specific applications like long short-term memory networks. These LSTMs use specific activations in different parts of the network for specific purposes. But other than that, in general, for a deep model, you should use something like rectified linear units or the leaky variant. But for the output neuron, it's a different case, because now you need to use that value to do something with it. And the kind of activation function that you're going to use will depend on what the purpose of your network is. So for regression, you need to predict a continuous value, and this value can go into any range. So you should not use an activation function. In a regression network, the last neuron should be just the linear combination of the previous layers, and you don't add a nonlinear activation function. This allows the neuron to learn whatever values you want it to learn in each example. For binary classification, sigmoid activation is a good choice, because now you can interpret that as the probability of the example belonging to some class. A probability needs to vary between 0 and 1, and the sigmoid function does that. So, if you use a sigmoid activation in the last neuron, this is only the last neuron, so there is not a big problem of having the vanishing gradients there. And it gives you an output that you can interpret as a probability between 0 and 1, so it's useful in that sense. If you use multi-class classification, what you need is you need output neurons in the same number as the classes that you have. So if you have 5 classes, you need 5 neurons. But it's also useful to have an idea of the probabilities of belonging to each class. So if you want to interpret the output of the network in that way, each neuron should only change between 0 and 1, and added all together, it should always add up to 1. That's how we could interpret it as the probability of belonging to any of the classes. So for that we can use softmax. Softmax uses this average with the exponential, and basically has this property. You have functions that always output within 0 and 1 for each neuron, and when you add them all up, they always add up to 1. So basically, you can use this softmax activation. Note that the softmax activation is not really an activation on a single neuron, it's on the whole layer, and it transforms the whole layer depending on the values of the neuron. But this is the best option for multi-class classification, because now if you have 5 classes, you obtain 5 outputs from the network, and each of these outputs is the probability of belonging to each of the classes. And they are all mutually exclusive, so they add up to 1. So the choice of activation for the output depends on what you're trying to do with the network. For the hidden layers, it should be something like rectified linear units to make it learn faster and not have the vanishing gradient problem.
The regression problem, why do you use sigmoid if we want a continuous?
No, regression is a linear output.
Oh,
Sigmoid is for binary classification. Okay, so binary classification is just one probability of belonging to one class. the rest is the probability of belonging to the other. For regression, use a linear output, and then for multi-class classification, use softmax. These are a few examples of rectified linear units that you have in TensorFlow. So the standard one, the concatenated, the leaky I didn't put the leaky one here, but there's also leaky ReLU there. There are a few strange ones. For example, this one is capped at 6, so it goes from 0 to 6 and then levels up again, which is counterintuitive because it looks like a sigmoid and it has also the 0 gradient at that part, so it shouldn't work, but actually works better in some specific cases. So there's always this problem that sometimes things work better in one way and not the other. But in any case, you have this one here. You can change the value at which it levels up, but the default is 6 because empirically it's what works best in one particular image classification problem. There are a few we're going to see later. Dropout is a bit stranger. It's used for regularization, but you have the softmax. You can use the linear one or just don't put any activation there, depending on how you build the graph. But you have lots of different possibilities here. So to sum up this part, you need to consider, depending on the data that you have, whether you're going for wider and shallower models, or if you want to use deep models. Remember the pros and cons. Typically, shallow models, even if they're wide, you need to take care of the features, so you cannot have features that are noise, and you need to have good features in order for the model to learn what you want. If you use deep learning, then typically the model will figure out what features to use in order to obtain better performance at whatever you're measuring. But the tricky part there is that you have no idea what features it's going to find. So one paradigmatic example here in the early stages of image recognition was training a model to distinguish between from pictures whether or not someone was standing close to a car. So you have either the car or the car with a person. And it managed an accuracy of 98% or something like that. But then they found out that they had taken the pictures of the cars in the morning and the person next to the car in the afternoon or something like that. And what the model was doing was just checking the illumination of the image, so if it was brighter or not, and that's how it was classifying the whole thing. So this is the problem when you don't know exactly which features the model is using. The activations. Remember that hidden layer activations are useful for breaking the linear combinations, and they should just be fast and not suffer from the vanishing gradient. For the output layers, you need to choose the one according to the kind of problem that you're trying to solve. Chapter 6 of the book is about this, and also you have the online help for TensorFlow on the activation functions. You have their explanations for more details.